So we have a mass, or a block, of mass m. And the only force on it is a spring force, F spring, given by negative kx. So by Newton's second law, we have that F net on the block is equal to mass times acceleration, and the only force on the block is the force of the spring, so that is equal to negative kx. Now, if we move everything to one side, we get that mass times acceleration plus kx is equal to 0. Now, recall that the acceleration is just the second derivative of the position with respect to time. So we actually have the mass times the second derivative of position with respect to time plus kx is equal to 0. Now, the initial spring stretch is x naught, so a good dimensionless variable to define is big X is equal to its position divided by x naught. And of course, both x and x naught have units of meters, so the units cancel out and big X is dimensionless. Now that means that x is equal to x naught times big X. So in our equation of motion, we have m times the derivative of, the second derivative of x naught big X over t dt squared plus kx naught big X equal to 0. Now, since x naught is a constant, we can factor that out of the derivative, and it'll cancel with this x naught, so we just get m times the second derivative of big X with respect to t plus k times big X equal to 0. And now if we divide by n, we get that the second derivative of big X with respect to t squared with respect to t plus k over m big X equal to 0. Now we want to define a suitable dimensionless variable big T so that this k over m disappears. Now notice that if we define big T as a function of little t, then by the chain rule for the second derivative of big X with respect to big T, with respect to little t, is equal to the second derivative of big X with respect to big T times the derivative of big T, first derivative of big T with respect to little t all squared, plus the first derivative of big X with respect to big T times the second derivative of big T with respect to little t. Now, big T will just be a constant multiple of little t, so the second derivative will disappear, which means that this term disappears. So all we have is that the second derivative of big X with respect to little t is the second derivative of big X with respect to big T times the derivative of big T with respect to little t all squared. So now we just need this squared to equal k over m so that we can factor out the k over m and just get d squared x over d big T squared plus x equals 0. So let us choose big T to equal the square root of k over m times t. Now this has dimensions 1 over time, and this has dimensions time, so big T is a dimensionless variable. So now, if we plug that into here, we have that d squared x over dt squared, little t squared, is equal to d squared x over d big T squared times the first derivative of big T with respect to little t, which is just the square root of k over m all squared. And that is equal to k over m times d squared x over d big T squared. So we have k over m times d squared over d squared x over d big T squared plus k over m big X is equal to 0. So now we just factor out the k over m, and we get that our equation of motion in terms of big X and big T is the second derivative of big X with respect to big T plus big X is equal to 0. So this is our big T, and this is our equation of motion.